What if everything you thought you knew about time was just a fraction of the truth? Picture a universe where time doesn't simply move forward in one straight line, but twists and folds into hidden dimensions, like secret corridors woven into the fabric of reality itself. This isn't science fiction, it's a real possibility that some of the brightest minds in physics are racing to unravel. For centuries, we've measured our lives in seconds, hours, and years, never questioning if there might be more to time than meets the eye. But what if the flow of time is just the surface of something far deeper and more mysterious? Think about the way a shadow hints at the shape of an object hidden from view. Time as we experience it could be just a shadow, a glimpse of something far grander and more complex. Scientists now suspect that beyond the familiar past, present, and future, there might be additional dimensions of time, curled up in ways we can't perceive, influencing everything from the birth of stars to the way we experience reality. Imagine a world where time behaves like a symphony, with layers of movement we've never noticed, where moments aren't just fleeting but connected in ways that defy logic. This is the frontier we're about to explore, a journey into the unknown where the very nature of existence might be rewritten. So why does this matter? Because if these hidden dimensions of time are real, they could hold the answers to some of the universe's greatest mysteries: dark energy, the fabric of space-time, even the origins of existence itself. We're standing at the edge of a revolution in how we understand reality, and today we're diving deep into 30 mind-blowing theories that could change everything. From the wild possibilities of time loops to the eerie notion that multiple timelines might exist alongside our own, this isn't just about science, it's about unlocking the secrets of the cosmos itself. So, are you ready to question everything you thought you knew? Let's begin. The block universe theory turns everything you think you know about time on its head. Instead of a river flowing from past to future, it suggests time is more like a frozen landscape where every moment from the Big Bang to the distant future already exists simultaneously. Picture a loaf of bread where each slice is a snapshot of the universe at a specific instant. To you, life feels like moving from one slice to the next, but in reality, the entire loaf is just there. This radical idea traces back to Einstein's theory of relativity, which shattered the notion of a universal now. For him, time wasn't absolute but woven into space-time, where your experience of it could stretch or compress depending on how fast you're moving or how close you are to a massive object. Take the famous twin paradox. One twin rockets off to space at near light speed while the other stays on Earth. When the traveling twin returns, they've aged far less than their sibling. In a block universe, this isn't just time dilation. It's proof that their lives are two fixed paths through space-time, with neither experience more real than the other. The past isn't gone, the future isn't unwritten. They're just coordinates in a vast cosmic map we're traversing. This flips our sense of free will upside down. If the future's already out there, are our choices an illusion? Some physicists argue yes, that the block universe paints a deterministic picture where every event is set in stone. Others counter that reality might be more like a branching tree, with every possible outcome existing in parallel. Either way, this theory forces us to confront a haunting question. Is time's flow just a trick of the mind, a way for our brains to make sense of a reality far stranger than we ever imagined? Now let's untangle another mind-bending perspective: eternalism versus the growing block theory. While the block universe treats all moments as equally real, eternalism takes it a step further by arguing that past, present, and future aren't just fixed coordinates but equally valid parts of reality. Think of it like a DVD. Every scene exists at once, even if you're only watching one frame at a time. Philosopher J.M.E. McTaggart famously challenged this view, splitting time into two competing sequences: the A series, where events flow from future to past, and the B series, where they're just static points in space-time. Eternalism embraces the B series, suggesting your childhood and your distant future are just as real as this very moment. But not everyone buys into this frozen cosmos. Enter the growing block theory, which paints time as a structure under construction. Here, the past and present exist like stacked bricks, while the future remains an open blueprint, unwritten and unreal. Picture a sculptor chiseling a statue. Every second adds a new layer to reality, but what's ahead is still raw marble. Proponents argue this avoids the eerie determinism of eternalism, leaving room for genuine unpredictability. Yet both theories stumble over the same paradox. If the future isn't real yet, why do the laws of physics seem to treat it as inevitable? Einstein's equations and quantum experiments keep nudging us toward eternalism, but the growing block holds a stubborn appeal. It feels true to how we experience life unfolding. Maybe the answer isn't a choice between the two, but a reminder that time's true nature might be too alien for our linear minds to grasp. After all, even light bends in the presence of a black hole. Why wouldn't time, but what gives time its unmistakable direction? That relentless march from past to future we take for granted. Enter the arrow of time, a concept rooted not just in philosophy but in the hard science of thermodynamics. At its core lies entropy, the measure of disorder in a system. Think of a sandcastle crumbling on the beach or ice melting in your drink. These everyday moments reveal a universe biased toward chaos, where energy disperses and systems evolve from order to disorder. That's the thermodynamic arrow of time, and it's why we remember yesterday but not tomorrow. Ludwig Boltzmann, the pioneering physicist who linked entropy to time's direction, faced a baffling paradox. The laws of physics, from Newton's mechanics to Einstein's relativity, are time-symmetric. Run them backward and they still hold true. So why does reality feel so irreversible? Boltzmann's answer was statistical. High entropy states are simply more probable. Imagine a deck of cards shuffled. It's disordered. Sorted by suit and number, it's improbably ordered. The universe, he argued, started in a rare low entropy state, the Big Bang, and we're witnessing the inevitable shuffle toward disorder. Yet this raises another puzzle. If time's arrow depends on entropy, could regions of the universe exist where time flows backward? Some theories suggest that in a hypothetical multiverse, pockets of decreasing entropy might create reverse arrows. Picture two mirrors facing each other, creating infinite reflections. If entropy defines time's direction, a mirrored universe might experience time in reverse, though we'd never perceive it, as our brains are wired by our own entropy-driven timeline. This isn't just theoretical gymnastics. The arrow of time shapes everything from the lifespan of stars to why we can't unbreak an egg. It even hints at a profound cosmic asymmetry. The universe had a beginning but may not have an end. And that might be the ultimate clue. Time's direction could be written into the very fabric of how reality unfolded from that initial, unimaginably ordered state. So next time you watch steam rise from your coffee, remember, you're not just seeing physics in action. You're witnessing the universe's deepest signature, the reason time feels like a one-way street. What if the past and future are nothing more than illusion stories we tell ourselves to make sense of existence? This is the radical heart of presentism, the theory that only the present moment is truly real. Unlike the block universe where all time exists at once, presentism argues that the past has vanished and the future is yet to be written. Everything you remember, every childhood photo, every prophecy, it's all just a mental reconstruction or speculation. The only thing that's concrete, according to this view, is the fleeting now. Think of it like a spotlight on a dark stage. The beam illuminates a single moment, your current experience, while everything behind and ahead fades into shadow. Physicists like Carlo Rovelli have taken this idea even further, suggesting time itself might not be fundamental. In his relational quantum mechanics framework, time emerges from interactions between particles, not as an independent force. It's why two atomic clocks in different gravitational fields tick at different rates. Time isn't universal but stitched together by local relationships. This clashes with our everyday intuition. Why does déjà vu feel so hauntingly familiar if the past doesn't exist? Presentism explains it as a glitch in perception, your brain misfiling a present experience as a memory. Even the flow of time, that relentless forward push, might be a trick of consciousness. Neuroscientists point out that our brains construct a seamless narrative from disjointed sensory inputs, editing delays into what feels like a continuous stream. A slap on the wrist registers pain before the sound of the hand clapping, yet we perceive them as simultaneous. Critics argue presentism can't reconcile with Einstein's relativity, where observers in motion or near massive objects experience time differently. If the present were absolute, how could two events be now for one person but not another? Yet presentism endures because it mirrors how we live, making choices, feeling regret, anticipating tomorrow, all anchored in the immediacy of this moment. Maybe time's greatest mystery isn't its hidden dimensions, but why it feels so real when the universe keeps hinting it might not be. Now, let's step into one of the most dizzying possibilities, that every choice you make doesn't just alter your future, but splinters time itself into infinite parallel realities. This is the heart of the many worlds interpretation, a radical take on quantum mechanics dreamed up by physicist Hugh Everett in the 1950s. Forget a single timeline here. The universe is a ceaselessly branching tree where every possible outcome plays out somewhere. Picture standing at a crossroads where turning left or right doesn't just lead you down different paths, it creates two entirely new versions of reality, each unfolding independently. Schrödinger's infamous cat trapped in a box with a 50-50 chance of survival takes on new meaning in this framework. In traditional quantum theory, the cat exists in a blur of superposition, both alive and dead, until someone opens the box and collapses its fate. But Everett's version flips the script. The moment you peek inside, reality splits. In one world, you find a purring cat, in another, a tragic outcome. Neither is more real than the other. They are equally valid branches on the cosmic tree. This isn't just about cats or trivial choices. Every quantum event, a particle's spin, a photon's path, sends ripples through the multiverse. Did you skip breakfast today? Somewhere, a version of you didn't. Did you hesitate before clicking this video? Another timeline exists where you scrolled past. The math behind this is staggeringly elegant. Instead of probabilities collapsing into one outcome, the universe's wave function simply keeps expanding, embracing every possibility. Critics argue this seems wasteful. Why would nature spawn countless unseen realities? But supporters counter that it's the simplest explanation for quantum weirdness, doing away with the need for mysterious observers to collapse outcomes. And if true, it means somewhere out there, every dream, every regret, every road not taken is playing out in a universe just as tangible as this one. The catch: these branches don't interact. You'll never meet your other selves, though some theories suggest quantum entanglement might hint at faint echoes between worlds. So where does that leave us? Either we're living in one thread of an infinitely woven tapestry, or the many worlds interpretation is a beautiful but untestable metaphor. Either way, it forces us to ask, if every possibility becomes real, does choice even mean anything anymore? Or are we all just travelers, wandering one path in an endless garden of forking timelines? What if time wasn't just a straight path but a tangled loop where the end circles back to the beginning? This is the bizarre promise of closed timelike curves, a twist in Einstein's general relativity where spacetime bends so severely that time itself forms a closed loop. Picture a record spinning on a turntable with a needle trapped in an endless groove. In this cosmic dance, you could theoretically travel forward in time only to return to your own past, like a snake biting its tail. The idea isn't just science fiction. In 1949, mathematician Kurt Gödel shocked the physics world by finding solutions to Einstein's equations where the entire universe rotates, twisting space-time into these mind-bending loops. Gödel's universe was more than a mathematical curiosity. It was proof that time travel might be stitched into the fabric of reality. But how? Imagine standing on a planet where every night you watch the stars trace the same patterns, not because they're fixed, but because the universe itself is revolving like a carousel. In such a place, if you set off on a rocket voyage along the right path, you could return before you left. Your future would become your past. Films like Interstellar flirt with this idea, where astronauts near the black hole Gargantua experience time dilation so extreme that hours for them stretch into decades back on Earth. But closed time-like curves go further. They erase the line between cause and effect entirely. This leads to the infamous grandfather paradox. What if you traveled back and prevented your own birth? Would you blink out of existence, making the trip impossible in the first place? Some physicists argue that quantum mechanics might offer an escape hatch. In the many worlds interpretation, your actions could spawn a new timeline, sidestepping the paradox. Others, like Nobel laureate Roger Penrose, suggest nature might enforce chronology protection, a cosmic rule that shreds any time loop before it forms, like a firewall against paradoxes. Yet the math stubbornly allows these loops to exist, especially near extreme objects like spinning black holes or cosmic strings. In theory, a sufficiently advanced civilization could harness these phenomena to build a time machine, bending space-time into a knot. But here's the catch: closed time-like curves demand perfect precision. A single misstep could unravel the loop or trap you in an infinite repeat, like a broken record skipping on the same beat. Whether these curves are hidden in the cosmos or forbidden by unseen laws, they force us to confront a chilling question. Is time's arrow just an illusion, a fragile rule that could shatter under the right conditions? Or does the universe guard its chronology like a dragon hoarding gold? One thing's certain: the mere possibility of time loops reveals how little we truly understand about the stage on which our lives unfold. Forget everything you know about crystals, those rigid, unchanging structures like diamonds or quartz. Time crystals are something far stranger, a form of matter that pulses in a never-ending dance, defying one of physics' most sacred laws, the arrow of time. First proposed in 2012 by Nobel laureate Frank Wilczek, these bizarre structures aren't just theoretical. In 2017, two separate teams of scientists brought them to life in labs, creating the first ever examples of matter that oscillates in a repeating cycle without any energy input. It's as if you wound up a clock once and it kept ticking forever. So how do they work? Picture a pendulum swinging back and forth in perfect rhythm. Normally, friction would slow it down, but a time crystal exists in a state where its atoms are perpetually shifting between configurations, locked in a rhythm that time itself can't disrupt. Unlike traditional matter, which settles into equilibrium, time crystals break what's called time translation symmetry. In plain terms, they don't play by the usual rules where time's flow smooths everything into sameness. Instead, they create their own microscopic heartbeat, a pulse that persists even at absolute zero, where all other motion should freeze. The secret lies in quantum entanglement, the spooky link between particles that Einstein famously hated. When atoms in a time crystal become entangled, their collective behavior locks into a pattern that repeats indefinitely, like a cosmic drumbeat echoing through the fabric of reality. This isn't perpetual motion in the old, debunked sense. It's a loophole in quantum mechanics where the system doesn't lose energy because it's already in its lowest possible state. It's not creating energy, it's redefining what stillness even means. The implications are staggering. Time crystals could revolutionize quantum computing, where stability is the holy grail. Quantum bits or qubits are notoriously fragile, collapsing at the slightest disturbance. but a time crystal's inherent rhythm might offer a way to protect them, like a metronome keeping a musician in perfect time. Imagine a quantum computer that doesn't just calculate faster, but does so with built-in error correction, its qubits shielded by the unshakable pulse of a time crystal lattice. Beyond technology, these structures force us to rethink time's fundamental nature. If matter can exist in a state that resists time's usual decay, what does that say about the universe's underlying rules? Could there be natural time crystals hiding in the cosmos, ticking away unnoticed? Some theorists speculate that neutron stars or exotic quantum fields might harbor similar behavior, blurring the line between matter and the arrow of time itself. Yet for all their promise, time crystals remain enigmatic. They can't power machines or break thermodynamics. Their motion is locked, useless for extracting work. But they're proof that time, even in its most rigid-seeming laws, has cracks where the unimaginable pokes through. In a universe where entropy reigns supreme, time crystals are tiny islands of order, whispering that time's grip might not be as absolute as we thought. And if that's true, who knows what other secrets are waiting to be uncovered? What if time isn't woven into the fabric of the universe at all, but is more like an illusion cast by something far simpler? This is the essence of the holographic principle, a theory so radical it suggests our three-dimensional reality, complete with the flow of time, might be nothing more than a projection from a two-dimensional surface. Picture a movie screen. The images appear lifelike with depth and motion, but peel back the curtain, and you'll find just a flat sheet of pixels. According to this idea, the universe could work the same way. Leonard Susskind, one of the principle's pioneers, first glimpsed this possibility while wrestling with black holes, those cosmic enigmas where gravity is so intense even light can't escape. Black holes posed a paradox. If you toss an encyclopedia into one, its information, every word, every page number should vanish forever, violating quantum mechanics' ironclad rule that information can't be destroyed. But Susskind and others realized something astonishing. The information isn't lost. It's imprinted on the black hole's event horizon, the point of no return, like a hologram etched onto its surface. Over time, this insight snowballed into a broader revelation. Maybe everything, stars, galaxies, even our experience of time, is encoded on a distant, two-dimensional boundary we can't see. How could this explain time? Imagine a computer simulation where the passage of time isn't fundamental but emerges from how data is processed. In the holographic universe, time might arise from quantum entanglement, the same spooky connection that links particles across vast distances. Every tick of the clock, every moment you perceive, could be a side effect of entangled bits of information updating on that hidden 2D surface. It's as if the universe is running on cosmic hardware where time is software, an emergent property rather than a built-in feature. This flips conventional physics on its head. Instead of time being a backdrop for events, it's more like a story being written in real time, with each entangled particle acting as a pen stroke in a vast cosmic narrative. The implications are dizzying. If true, our perception of past, present, and future might be as superficial as the depth in a hologram, convincing but not fundamental. Even the Big Bang could be reinterpreted as a glitch in the code, a moment when the projection flickered into existence. Critics argue the holographic principle remains speculative, lacking direct observational proof. But experiments with quantum gravity and black hole simulations keep nudging us toward this strange reality. If time is truly emergent, it means we're not just witnesses to the universe's unfolding but participants in a grand illusion, one where the boundaries of space, time, and dimension are far more fluid than we ever imagined. Imagine a universe where beginnings and endings don't exist, only an endless loop of creation and destruction, like a cosmic heartbeat pulsing across eternity. This is the essence of cyclic time, a concept as ancient as human civilization yet startlingly alive in modern physics. Long before telescopes peered into deep space, Hindu cosmology envisioned time as a wheel, turning through epochs called yugas, each lasting millions of years. The universe, they believed, wasn't born once but reborn infinitely, with each cycle emerging from the remnants of the last. Even the Mayans and ancient Greeks flirted with similar ideas, seeing time not as a line but a circle, where history repeats itself in grand, unknowable rhythms. Fast forward to today, and science is flirting with a strikingly similar vision. Enter the Big Bounce, a theory that reimagines the Big Bang not as the absolute beginning but as a rebound from a previous universe's collapse. Picture a rubber band stretched to its limit. When it snaps back, it doesn't vanish. It recoils, ready to stretch again. In this model, our expanding universe might one day halt, reverse, and implode into a searing hot singularity, only to explode outward anew in another Big Bang. The math behind this is rooted in loop quantum gravity, where space-time isn't infinitely divisible but woven from tiny, indivisible threads. At the moment of collapse, these threads resist further compression, creating a repulsive force that bounces the universe back into existence. Roger Penrose, the visionary physicist behind black hole singularities, took this even further with his conformal cyclic cosmology. He proposes that universes don't just bounce, they reset. In the distant future, when all matter has evaporated into radiation and black holes have decayed away, the universe becomes a featureless sea of particles so spread out that distance and time lose meaning. At this point, Penrose argues, the universe's end becomes indistinguishable from its beginning, allowing a new Big Bang to emerge from the ashes, the eerie evidence. Circular patterns in the cosmic microwave background, which Penrose interprets as gravitational shockwaves from a pre-Big Bang universe. Yet the linear Big Bang model still dominates, backed by the universe's observed expansion and the afterglow of creation, the cosmic microwave background. This radiation map shows a strikingly uniform early universe, a hallmark of rapid inflation that's hard to reconcile with cyclic theories. Critics argue that without a mechanism to smooth out entropy between cycles, each bounce would grow messier, like a photocopy of a photocopy, degrading over eons. But proponents counter that quantum effects or unknown physics might reset entropy at each rebirth, preserving the universe's order like a cosmic spring cleaning. The stakes couldn't be higher. If cyclic time is real, our universe is just one page in an infinite cosmic storybook with no true beginning or end. It challenges not just our scientific models but our very sense of place in the cosmos. Are we living in the first chapter or the trillionth? The answer might lie hidden in the faint whispers of the microwave background or the quantum ripples of spacetime itself. Until then, the allure of cyclical time endures, offering a humbling vision of eternity where every ending is just a prelude to another dawn. Time isn't just something we measure, it's something we experience, and Einstein's theory of relativity shattered the illusion that this experience is universal. Imagine two identical clocks, one placed on a mountain, the other at sea level. Over time, they'll tick at different rates, not because they're broken, but because gravity literally bends time itself. This is time dilation in action, a phenomenon so precise that GPS satellites orbiting Earth have to account for it. If they didn't adjust their onboard clocks for the weaker gravity and faster motion in space, your navigation apps would be off by miles within minutes. Think about the astronauts aboard the International Space Station. Orbiting at 17,000 miles per hour, they're moving fast enough and far enough from Earth's gravity that time actually passes slightly slower for them than for us on the ground. Over a 6-month mission, they age about 0.007 seconds less than the rest of humanity. It's a tiny difference, but it's measurable proof that time isn't a rigid backdrop to the universe. It's fluid, stretching and compressing like taffy depending on speed and gravity. The real mind bender, this isn't just about clocks. Your body is a collection of biological processes all governed by time. If you could hover near the edge of a black hole where gravity warps time to an extreme, you might watch centuries pass on Earth in what feels like minutes. The sci-fi trope of cryogenic freezing pales in comparison. Relativity offers a way to time travel into the future without any technology, just physics. Of course, you'd never feel time slowing down in the moment. To you, everything would seem normal. It's only when you return to a less warped environment that you'd see the difference, like stepping out of a time machine into a world that's moved on without you. What's truly humbling is how ordinary these effects are. Time dilation isn't some exotic rarity, it's happening right now, all around us. Every time you take a step, the atoms in your moving foot experience time infinitesimally slower than those in your stationary head. It's too small to notice, but it's there, woven into the fabric of reality. Even the glow of your smartphone screen is subtly shifted by gravity's grip on time. Photons from the top of the screen reach your eyes ever so slightly faster than those from the bottom. Einstein's revelation wasn't just about correcting clocks or explaining space travel quirks. It rewrote our understanding of existence, proving that time and space are threads in the same tapestry, endlessly intertwined. The next time you check your GPS or watch a rocket launch, remember, you're not just seeing technology at work. You're witnessing the universe's hidden choreography, where time itself dances to the tune of gravity and motion. And in that dance, every tick of the clock is a reminder that reality is far stranger and far more wondrous than our everyday lives suggest. What if the most fundamental laws of the universe don't include time at all? The Wheeler-DeWitt equation, a cornerstone of quantum gravity, dares to suggest just that. A universe where time isn't a building block of reality, but an illusion that emerges from deeper, timeless physics. Named after physicists John Wheeler and Bryce DeWitt, this controversial equation attempts to unify Einstein's general relativity with quantum mechanics by erasing time from the mathematical framework entirely. Imagine writing the ultimate recipe for the cosmos, only to realize one key ingredient, time, never belonged in the mix. Julian Barber, the iconoclastic physicist behind The End of Time, champions this radical view. He argues that our perception of time's flow is like watching individual frames of a movie and mistaking the sequence for movement. In reality, Barber suggests, the universe might consist of a vast collection of static nows called time capsules, snapshots that our brains stitch together into the illusion of continuity. It's as if every moment is a frozen sculpture in a cosmic gallery, with no actual passage between them. The math behind this idea is as elegant as it is disorienting. The Wheeler-DeWitt equation describes the quantum state of the entire universe without referencing time at all. Instead of a dynamic process, it treats reality like a single, unchanging equation, a cosmic still life where change is just a trick of perspective. This aligns with the problem of time in quantum gravity, a puzzle that arises when trying to reconcile relativity's elastic spacetime with quantum mechanics' discrete jumps. If both theories are correct, why does one treat time as malleable while the other seems to erase it? Critics argue that dismissing time flies in the face of lived experience. How can we reconcile a timeless universe with the undeniable sensation of aging, of seasons turning, of stars being born and dying? Barber's answer lies in complexity. Just as temperature emerges from the chaotic motion of molecules, none of which individually possess heat, time might emerge from the intricate relationships between quantum events. The universe's sheer scale could create the appearance of flow, even if the underlying reality is static. Yet the debate rages on. Some physicists propose that time isn't absent but hidden, woven into the fabric of quantum entanglement or encoded in the holographic boundary of spacetime. Others see the Wheeler-DeWitt equation as a mathematical artifact, a sign that our theories are incomplete rather than revelatory. After all, if time isn't fundamental, why does it feature so prominently in every other physical law? The implications are profound. A timeless universe could redefine causality, free will, even the nature of existence itself. If time isn't real, is the past just a memory and the future a projection? Or are all moments equally valid, like points on a map we're traversing in an order that only feels inevitable? The Wheeler-DeWitt equation doesn't just challenge our theories, it forces us to confront whether time itself is the ultimate cosmic mirage, a story we tell ourselves to make sense of a reality far stranger than we ever imagined. In the quantum realm, where particles flicker between states like candle flames in the wind, time might not be a fundamental feature, but something that emerges from the universe's most mysterious connection, quantum entanglement. Picture two coins spinning in separate corners of the universe, eternally linked so that when one lands heads up, the other always shows tails, no matter the distance. This spooky action at a distance, as Einstein called it, might hold the key to why we experience time's flow at all. Recent breakthroughs in quantum physics suggest entanglement doesn't just correlate particles, it could weave the very fabric of causality. The ER equals EPR conjecture, a daring idea proposed by physicists Juan Maldacena and Leonard Susskind, takes this further by linking entanglement to wormholes. Here's the wild part: when two particles become entangled, it's as if a microscopic wormhole, a shortcut through space-time, connects them. These hypothetical tunnels, known as Einstein-Rosen bridges, might share an unexpected kinship with the way entangled particles, EPR pairs, communicate instantaneously. In other words, entanglement isn't just a quantum quirk, it could be space-time stitching, with time emerging from these hidden threads. Lab experiments are now putting this idea to the test. In 2019, researchers at the University of Maryland and Harvard simulated entangled particles using quantum computers and observed patterns resembling space-time dynamics. When they adjusted the degree of entanglement, the simulation's time sped up or slowed down, as if the particles' connection was dictating the flow itself. Another team at Caltech found that entangled systems naturally encode a directionality, an arrow of time, even when the underlying physics is symmetric. It's like watching a deck of shuffled cards spontaneously sort itself. The more entangled the particles, the more the system leans toward order, creating the illusion of time's forward march. What does this mean for our everyday experience? If time emerges from entanglement, then the universe might not keep time at its deepest level. Instead, the rhythms we perceive, clocks ticking, seasons changing, could be collective effects like the roar of a crowd emerging from individual voices. This flips the script on how we understand reality. Black holes, for instance, might not destroy information but scramble it into entangled states, preserving it in ways we're only beginning to decipher. Even the Big Bang could be reinterpreted as a moment when the universe's primordial quantum links crystallized into the space-time we recognize today. Yet mysteries remain. If entanglement underpins time, why do we perceive it as smooth and continuous, not flickering or disjointed? Some theorists propose that decoherence, the process by which quantum systems interact with their environment, averages out the microscopic jumps into the steady flow we experience. Others suggest time's emergence might resemble temperature. Just as heat arises from countless atomic collisions, time could be a statistic, a large-scale phenomenon invisible at the quantum scale. The implications are staggering. If true, this could unify quantum mechanics and general relativity, two foundational theories that have resisted reconciliation for a century. It also hints at a universe far more interconnected than we ever imagined, where every tick of the clock is a whisper between entangled particles, weaving the tapestry of reality itself. So the next time you glance at a watch, remember, you might not just be measuring time, you're witnessing the echo of quantum bonds vibrating across the hidden dimensions of existence. What if the universe has a built-in rulebook for time travel, one that ensures no matter how hard you try to alter the past, reality will always course correct to avoid contradictions? This is the spine-tingling premise of the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. Unlike chaotic time travel tales where stepping on a butterfly erases civilizations, Novikov's universe runs on an ironclad law. Every action taken in the past must already be part of history. Imagine dropping a pebble into a river. The ripples don't rewrite the water's flow, they were always meant to be there. Take the film Predestination, where a time-traveling agent's attempts to change events only cement them into place. Every decision, every meeting, every betrayal turns out to be an inescapable part of a loop that was always happening. Novikov argued that time travel, if possible, would function exactly like this. Any paradox gets smoothed out by the universe's hidden logic. If you travel back to prevent your parents from meeting, some quirk of fate, a missed train, a sudden storm, will ensure they cross paths anyway. The past isn't a fragile vase you can shatter. It's a self-healing organism bending to preserve its own consistency. But how does this square with Hawking's chronology protection conjecture, which posits that the laws of physics outright forbid time travel to prevent paradoxes? Hawking famously quipped that if time machines were possible, we'd have been overrun by tourists from the future. His idea hinges on quantum effects like vacuum fluctuations near wormholes that would destabilize any time loop the moment it formed. It's nature's way of slamming the door on paradoxes before they can occur. Novikov's principle counters this by claiming paradoxes never arise in the first place. The universe doesn't need to block time travel because it's inherently self-correcting. Think of it like a cosmic game of Jenga. No matter which block you pull, the tower won't collapse because the rules won't let you make a move that topples it. This isn't just philosophical hand-waving. Some quantum models support the idea. In certain interpretations, particles traveling back in time adopt states that reinforce rather than disrupt the timeline. Critics argue this feels suspiciously like destiny in a physicist's lab coat. If every time-traveling act is predestined, does free will evaporate? Not necessarily. Novikov's principle doesn't dictate how events unfold, just that they must remain consistent. You might choose to climb a mountain or write a symphony, but if your time tinkering affects those choices, the universe ensures the outcome aligns with what already happened. The debate between these two giants, Novikov's elegant consistency and Hawking's staunch prohibition, reveals just how thorny time travel is. Is reality a flexible tapestry that adjusts to our meddling, or a fortress guarded by unbreakable laws? Until we crack quantum gravity or stumble upon a wormhole, these theories remain thrilling thought experiments. But one thing's certain: if time travel is possible, the universe has already accounted for it, and every move we make was written into the script long before we thought to act. What if nearly 3 centuries of human history never actually happened? That's the startling claim at the heart of the phantom time hypothesis, a fringe theory proposing that the years 614 through 911 were entirely fabricated. According to this audacious idea, concocted by German historian Herbert Illig in the 1990s, rulers and scholars of the Middle Ages conspired to insert these phantom years into the calendar, erasing events, inventing rulers, and rewriting timelines to suit political agendas. It's a premise that sounds ripped from a conspiracy thriller, but Illig argued his case with surprising detail, pointing to gaps in archaeological records and inconsistencies in dating methods. The theory zeroes in on the reign of Holy Roman Emperor Otto III and Pope Sylvester II, who allegedly orchestrated this grand historical forgery to position themselves at the symbolic year 1000. By Illig's logic, artifacts and documents from this period were either backdated or fabricated, creating the illusion of a timeline that never was. He even suggested that iconic figures like Charlemagne might be composite characters, stitched together from legends to fill the manufactured gap. It's a narrative that plays on our deepest suspicions about power, who controls history and for what ends, but science pushes back hard. dendrochronology, the study of tree ring patterns, offers a particularly devastating rebuttal. Trees don't lie. Their growth rings record environmental conditions year by year, creating unbroken sequences that stretch back millennia. By cross-referencing overlapping samples from ancient wood, researchers have constructed timelines that align seamlessly with traditional historical records, no 300-year void in sight. Carbon dating further crushes the hypothesis, with consistent radioactive decay markers across artifacts from the missing centuries. Even celestial events like solar eclipses, meticulously documented in Chinese and Middle Eastern texts, match conventional dating with no gaps. Yet the phantom time hypothesis endures in pop culture and online forums, tapping into something primal: our fascination with hidden truths and the fragility of knowledge. It's the historical equivalent of questioning whether we're living in a simulation, unsettling, unprovable to some, and irresistible to debate. Mainstream historians dismiss it as pseudo-history, but its persistence reveals how easily the past can feel like a hall of mirrors where certainty wobbles under scrutiny. After all, if 300 years could vanish without a trace, what else might we have gotten wrong? Perhaps the theory's real value lies not in its credibility, but in the questions it forces us to ask. How do we verify what we think we know? Who gets to write history and whose stories are erased? In an age of deepfakes and digital revisionism, the phantom time hypothesis is less about the Middle Ages and more about our own anxieties, the fear that reality itself might be more malleable than we dare admit. What if time isn't just part of the four-dimensional fabric of space-time, but something even grander, a fifth dimension hidden in plain sight? This idea isn't just wild speculation. It's a serious proposal woven into some of the most ambitious theories in physics. Picture space-time as a vast four-dimensional tapestry, 3 dimensions for space, 1 for time. But what if that tapestry is just a single thread in a much larger cosmic weave, with time extending beyond our perception like a shadow we can't quite see? One of the earliest hints of this possibility came from Kaluza-Klein theory, a bold extension of Einstein's general relativity. In the 1920s, Theodore Kaluza proposed that if you add a 5th dimension to the equations, something miraculous happens. Gravity and electromagnetism unite into a single force. Imagine a flute with an invisible extra hole. Blow into it just right and you'll hear harmonies no one knew were possible. Kaluza's 5th dimension was like that hidden hole, curled up so tightly we'd never notice it. But here's the twist. Later interpretations suggested this extra dimension might not just be spatial. It could represent a hidden layer of time, a direction we don't experience but that influences the universe in ways we're only beginning to grasp. String theory takes this even further, suggesting there might be not one but several extra dimensions, some spatial, some possibly temporal. Think of it like this: if our universe is a sheet of paper, these extra dimensions would be folded into origami creases, invisible to us but shaping reality at every turn. In this framework, time could be more than a linear flow. It might have textures and folds we can't perceive, like a melody playing in harmonies our ears aren't built to hear. To grasp how this might work, consider the classic flatland analogy. Imagine beings living in a 2-dimensional world, unaware of the 3rd dimension. To them, a sphere passing through their plane would appear as a circle that grows and shrinks mysteriously. Now extrapolate that to our 4-dimensional existence. A 5th-dimensional time might interact with us in ways we misinterpret as random quantum fluctuations or even dark energy phenomena we can measure but can't yet explain. Could this higher-dimensional time help solve some of physics' biggest puzzles? Some researchers think so. Dark energy's relentless push, accelerating the universe's expansion, might be the gravitational leakage from this hidden temporal dimension. Quantum entanglement's spooky action at a distance could be particles communicating through folds in higher dimensional time, bypassing our conventional spacetime entirely. Even the arrow of time itself, why entropy always increases, might be a shadow of deeper dimensional dynamics. Yet the challenge remains: how do we detect something so fundamentally beyond our senses? Experiments like the Large Hadron Collider hunt for evidence of extra dimensions in particle collisions, searching for missing energy that might vanish into hidden realms. Other proposals suggest studying gravitational waves for subtle anomalies, like ripples that behave as if they're brushing against unseen structures. The wildest implication: if time is a higher dimension, our experience of it might be like a fish mistaking the ocean's surface for the entirety of water. There could be currents, depths, even entire directions of time we're oblivious to, shaping reality in ways we're only starting to imagine. And if that's true, the future of physics might not just be about discovering new particles or forces, but unlocking the very architecture of time itself. The quantum world doesn't just bend the rules of time, it shatters them entirely. Enter the transactional interpretation, a radical theory where quantum waves don't merely exist in the present but crash through time like ripples in a pond flowing both forward and backward. Proposed by physicist John Cramer in the 1980s, this idea reimagines quantum mechanics as a cosmic handshake between past and future, where particles send signals backward in time to confirm their own existence. Picture throwing a ball into the air only to watch it descend before your hand releases it. That's the level of temporal acrobatics we're dealing with here. At the heart of this theory are alpha waves and confirmation waves, quantum signals that propagate forward and backward through time, negotiating reality's outcomes like celestial diplomats. When an electron jumps between energy levels, it doesn't just leap, it sends an alpha wave into the future, which then echoes back as a confirmation wave, finalizing the event. This isn't just philosophy, it's a mathematical framework that predicts quantum behavior with eerie accuracy. The implications are staggering. Every quantum interaction might involve a fleeting conversation across time itself, where the future whispers back to the past to seal the deal. This gets even wilder when you consider the delayed choice experiment, a quantum test that feels like a prank played by reality. Imagine shooting photons through a double-slit apparatus one at a time. If you measure which slit each photon passes through, it behaves like a particle no-interference pattern. But if you don't measure, it acts like a wave, creating an interference pattern. Here's the kicker: you can wait until after the photon has theoretically chosen its path to decide whether to measure it. It's as if the photon's past behavior changes based on your future decision. Cramer's interpretation explains this by suggesting the confirmation wave, traveling backward, adjusts the photon's history to match the final experimental setup. The present isn't just shaped by the past, it's haggle with the future. Then there's the quantum eraser, an experiment so mind-bending it makes the delayed choice look tame. Scientists can erase information about a photon's path after it's been detected, causing the interference pattern to reappear. In Cramer's terms, the erasure sends new alpha waves backward, rewriting the photon's history to align with the new experimental conditions. It's like editing a document you already sent, except the universe obliges by retroactively changing the original. Critics argue this interpretation smacks of retrocausality, where effects precede causes. But supporters counter that it's no weirder than quantum entanglement or superposition, just less familiar. After all, if the math works and the predictions hold, who's to say time doesn't flow both ways at the quantum scale? What's truly unsettling is how this challenges our bedrock notion of free will. If future measurements influence past events, are our choices really ours? Or is the universe a vast, self-correcting puzzle where every piece clicks into place only when the last one is set? The transactional interpretation doesn't just tweak our understanding of time. It forces us to confront whether time, as we know it, is even the right framework for reality's deepest layers. Maybe the cosmos isn't a clock ticking forward, but a kaleidoscope where every twist reconfigures not just the present but the past itself. Julian Barber's radical vision of reality starts with a simple, haunting question. What if time isn't real? Imagine stepping into a gallery where every painting is a frozen moment, a child's laugh, a supernova's explosion, your first heartbeat, each frame complete unto itself with no before or after. This is the essence of Barber's timeless universe, where what we perceive as the flow of time is just an illusion stitched together by our brains. He calls these frozen moments time capsules, isolated snapshots that create the appearance of continuity, like flipping through a stack of photographs and mistaking the sequence for motion. Barber's idea didn't emerge from nowhere. It's rooted in a deep frustration with physics' reliance on time as a fundamental variable. Einstein's equations treat time as flexible but still essential, while quantum mechanics stumbles over how to define its role at microscopic scales. The Wheeler-DeWitt equation, which describes the quantum state of the entire universe, conspicuously lacks a time parameter altogether. For Barber, this wasn't a mathematical quirk but a clue, a sign that time might be emergent, like temperature arising from the chaos of molecules. To grasp his theory, think of a cosmic jukebox where every possible configuration of the universe exists as a standalone now. Your life isn't a movie playing from birth to death. It's a collection of disconnected scenes that only seem connected because your brain arranges them into a narrative. This mirrors quantum mechanics' many configurations approach where particles don't have definite positions until measured. Barber takes this further, suggesting the whole universe exists in a superposition of static states with no actual progression between them. Critics pounce on the obvious question: if time is an illusion, why do we all experience aging, decay, and cause and effect so vividly? Barber's answer lies in complexity. Consider how a flock of birds creates the illusion of a swirling shape in the sky. No single bird directs the motion, yet the pattern emerges spontaneously. Similarly, sequences of time capsules might arrange themselves into structures that look like a flowing timeline, even though no underlying river of time exists. The universe's sheer scale and interconnectedness could generate the mirage of duration like a cosmic sleight of hand. The implications ripple across physics. Cosmology's reliance on a beginning, the Big Bang, gets upended. In Barber's framework, the start of the universe is just one time capsule among infinite others with no privileged status. Even entropy, the cornerstone of time's arrow, becomes a local phenomenon, a feature of certain configurations rather than a universal law. This could resolve lingering puzzles like why the early universe had such unnaturally low entropy. Perhaps it wasn't a starting point at all, but a statistical fluke in an eternal mosaic of moments. Yet the theory faces fierce opposition. Relativity depends on time's flexibility, not its absence. Black holes evaporate, stars collapse, and quantum states evolve, all processes that scream change. How can change exist without time? Barber's supporters counter that what we call change might be patterns across capsules, like seeing different frames of a film without acknowledging the real. But even they admit the hardest sell is consciousness itself. Our minds are wired to experience time as a flow, a stubborn perception that resists pure mathematics. Barber's timeless universe forces us to confront a profound irony. The very thing that structures our existence might be the ultimate illusion. If he's right, the past isn't gone and the future isn't waiting. They're simply other rooms in a vast, unchanging mansion we'll never fully explore. And perhaps that's the most unsettling truth of all. Time's greatest trick isn't passing. It's convincing us it was ever there at all. If time were a film strip, Planck time would be a single frame, the smallest possible snapshot the universe allows. Clocking in at around 10 to the power of minus 43 seconds, this unimaginably brief interval isn't just a mathematical quirk, it's the cosmic stopwatch's ultimate limit. According to quantum theory, trying to measure anything shorter would require so much energy it'd collapse into a black hole, shredding the very fabric of reality. This is where time stops being smooth and reveals its grainy, pixelated underbelly, a revelation that could rewrite our understanding of existence. Enter loop quantum gravity, one of the boldest attempts to unify relativity and quantum mechanics. Unlike string theory's tiny vibrating threads, this framework proposes that spacetime itself is woven from finite, interlocking loops. Think of a mesh screen where each intersection is a quantum of spacetime. At this scale, time doesn't flow like a river but jumps between these discrete Planck-sized moments like a cosmic flipbook. The implications are staggering. Just as your digital photos lose clarity when zoomed in too far, reality itself might dissolve into individual pixels beyond Planck time. This digital universe hypothesis doesn't just challenge our metaphors, it confronts the paradox of infinity head-on. Classical physics treats spacetime as infinitely divisible, but loop quantum gravity suggests there's a bottom floor to reality. Imagine trying to divide a centimeter into smaller and smaller pieces. Eventually, you'd hit a wall, a fundamental unit where smaller becomes meaningless. Time, in this view, operates the same way. No infinite regress, no paradoxes, just a universe built on irreducible quantum steps. But how would this granularity affect everyday experience? Surprisingly, not at all. Just as you don't notice individual pixels on a high-resolution screen. The Planck scale is so minuscule that even the fastest atomic processes span billions of these ticks. Yet this hidden structure could solve one of cosmology's biggest headaches, the singularity at the Big Bang. If time is quantized, there's no true zero moment, just a smallest possible interval before which nothing, not even time, existed. No infinite densities, no breakdown of physics, just the first click of the cosmic clock. Critics argue this model lacks experimental proof. After all, probing Planck-scale phenomena requires energies trillions of times beyond our particle colliders. But supporters point to indirect hints, like anomalies in gamma-ray bursts that might reveal spacetime's granularity. Others suggest the universe's accelerating expansion could be a macroscopic echo of these microscopic quantum jumps. The wildest implication: if time is digital, reality might literally compute itself into existence, with each Planck tick representing a cosmic processor cycle. It's a vision that blurs the line between physics and philosophy, one where the universe isn't just described by math but might fundamentally be math in motion. So the next time you check your watch, remember, beneath its smooth sweep lies a hidden lattice of quantum moments ticking away in the heart of everything. Philosophers and physicists have wrestled for centuries with a fundamental question: does only the present moment exist, or are past, present, and future equally real? The B theory of time throws its weight behind the latter, proposing a universe where every moment from the Big Bang to the heat death of the cosmos exists simultaneously, like frames in an endless film reel. Unlike presentism, which treats the present as the only tangible reality, the B theory insists that your childhood, your next birthday, and the distant future are all just fixed coordinates in spacetime, no more or less real than one another. This radical view finds unexpected support in Einstein's theory of relativity, where time isn't an absolute river but a flexible dimension woven into the fabric of the universe. Think of spacetime as a vast library where every event in history is a book sitting permanently on the shelf. From your perspective, you're only reading one page at a time, but the entire collection already exists. This explains why two observers moving at different speeds or in different gravitational fields can disagree on the order of events, a phenomenon called relativity of simultaneity. Imagine two lightning bolts striking a train's front and back. To a passenger aboard, they might appear simultaneous, but to someone on the platform, one strike occurs first. In a B-theory universe, this isn't a contradiction. Both sequences are equally valid because time isn't flowing. It's just laid out, with every moment eternally present in the grand structure of space-time. Metaphysics has clashed fiercely over this idea. Presentists argue that treating all times as equally real drains meaning from concepts like change and free will. If the future is already out there, how can our choices matter? B-theorists counter that causality isn't about temporal flow but logical connections between events. Your decision to drink coffee this morning may be fixed in space-time, but it's still causally linked to your alertness later, a relationship that doesn't require time to move. It's like connecting dots on a map. The path exists all at once, but the order of drawing matters for understanding the journey. The debate grows thornier when quantum mechanics enters the picture. Quantum experiments like delayed choice tests suggest particles can retroactively alter their past behavior based on future measurements. A headache for presentism, but oddly compatible with the B-theory's timeless landscape. If all moments are equally real, then quantum weirdness might just be hidden threads stitching together disparate parts of the cosmic tapestry. Yet the B-theory's greatest strength, its harmony with relativity, is also its biggest hurdle for human intuition. We're wired to experience time as a relentless forward march, not a static panorama. Reconciling this with physics demands a Copernican scale shift. Just as Earth isn't the center of the universe, our perception of time might not reflect its true nature. Whether the B-theory ultimately prevails or not, it forces us to confront a humbling truth: reality's structure may be far stranger than the stories our brains tell to navigate it. At the quantum level, time's arrow might not be dictated by entropy alone, but by the mysterious moment when possibilities collapse into reality. This idea hinges on the wave function, the mathematical heartbeat of quantum mechanics that describes particles as clouds of probability. An electron isn't just here or there, it exists in a haze of potential positions until measured, at which point the wave function collapses into a definite state. Some physicists, like Roger Penrose, argue this collapse isn't just a quirk of observation, it's the engine of time's irreversible flow. Penrose's objective collapse theory proposes that wave functions collapse spontaneously due to gravity's subtle tug, not just human intervention. Picture a house of cards trembling under its own weight until one breath topples it. In this view, quantum systems teetering between states eventually succumb to gravity's whisper, snapping into reality and generating the irreversible clicks that build up into time's arrow. The implications are profound. Every collapse would leave tiny ripples in space-time, like footprints in the sand marking the path from past to future. Experiments aiming to detect these ripples, like ultra-sensitive gravity wave detectors, could one day test this radical idea. But why would collapse create time's direction? The answer lies in entanglement. Before collapse, particles exist in a superposition of states, their futures branching like a maze. The moment one particle's state is determined, its entangled partners instantly resolve too, no matter how far apart. This sudden synchronization creates a cascade of nows that can't be undone, a one-way street carved by quantum decisions. It's as if the universe plays a game of dominoes where knocking over the first tile sets off a chain reaction that defines the forward march of time. Alternative interpretations, like the many worlds theory, sidestep collapse entirely. Every possible outcome branches into a new universe, leaving no single timeline to privilege an arrow of time. Yet Penrose's approach offers an elegant solution to entropy's puzzle. Collapse events naturally increase disorder, aligning with thermodynamics' second law. Each time a wave function collapses, information about the discarded possibilities is lost, seeding the universe with the randomness that fuels entropy's rise. The search for experimental proof is already underway. Labs are constructing supercooled nanoscale objects to observe if gravity truly triggers collapse, while others analyze the cosmic microwave background for patterns that might bear collapse's fingerprints. If these efforts succeed, they could bridge quantum mechanics and general relativity, not just explaining time's arrow but revealing it as a quantum gravitational phenomenon. What's striking is how this flips the traditional narrative. Instead of time emerging from cosmic scale thermodynamics, its direction might be built from the ground up, trillions of quantum collapses per second, each a tiny stitch in the fabric of causality. Whether Penrose's vision holds or not, it forces us to consider that time's flow might not be imposed from above but forged in the quantum fires where reality itself is decided. Aristotle once pondered whether time could be chopped into indivisible chunks, tiny, unbreakable moments he called chronons. Fast forward 2 millennia, and modern physics is wrestling with the same radical notion. What if time isn't a smooth, continuous flow but a series of discrete steps like frames in an old film reel? This is the chronon hypothesis, a theory that dares to pixelate time itself. Imagine the universe not as a river but as a cosmic flipbook where reality flickers between static snapshots too fast for us to notice. The implications are staggering if true. It means every tick of the clock, every beat of your heart, is actually hopping between these invisible quantum moments. At first glance, this clashes violently with classical physics. Newton's laws and Einstein's relativity treat time as infinitely divisible, a backdrop against which motion unfolds seamlessly. Even Schrödinger's famous equation, which governs quantum mechanics, assumes time is a smooth variable, a canvas for probability waves to ripple across. But here's the twist. When you zoom into the Planck scale, where space and time supposedly fray into quantum foam, the math starts to sputter. Attempts to merge general relativity with quantum mechanics keep hitting a wall, and some theorists suspect the problem isn't the equations but the very assumption that time is continuous. Enter the modern chronon, a hypothetical quantum of time with a duration around 10 to the minus 43 seconds, the Planck time. In this framework, time isn't a flowing river but a staircase, with each step representing the smallest possible interval. Just as pixels limit how finely you can zoom into a digital image, chronons would impose a fundamental resolution on reality. No events could be shorter than this, no causes and effects crammed into smaller gaps. It's as if the universe has a refresh rate and we're all living inside its flickering display. Critics pounce on a glaring issue. If time is granular, how do we explain motion? A ball flying through the air would, between chronon ticks, seem to teleport infinitesimally forward, violating our intuition of smooth movement. But supporters counter that this might explain quantum jumps, where electrons shift orbits without traversing the space in between. Perhaps what we perceive as motion is just a succession of quantum snapshots, stitched together by our brains into an illusion of continuity. Even consciousness itself might rely on this trick, with our minds editing discrete moments into the seamless stream we call now. The debate gets thornier when applied to cosmology. If time is quantized, the Big Bang's singularity, a moment of infinite density, becomes nonsensical. Instead, the universe's birth might resemble the first frame of a film, with no before to speak of. Some models even suggest chronons could solve black hole paradoxes, preventing information loss by imposing a smallest possible unit on spacetime's fabric. Yet for all its elegance, the chronon hypothesis remains on the fringe. No experiment has detected time's graininess, and many physicists argue that existing theories work too well to need such a radical overhaul. But history whispers caution. Once, atoms were just philosophy and quantum jumps seemed absurd. Whether chronons are real or not, they force us to confront a humbling truth. Time, the most familiar dimension, might be the one we understand least. And if Aristotle's ancient intuition holds, reality's true rhythm could be hiding in the spaces between the ticks we've always taken for granted. What if the flow of time isn't a fundamental feature of reality, but lines of code in an unimaginably advanced simulation? This unsettling possibility sits at the heart of simulation theory, where even time itself might be a programmed variable, a cosmic clock ticking at the speed set by some higher dimensional programmer. Nick Bostrom's famous trilemma lays out the chilling math. Given enough technological advancement, future civilizations could have the computing power to create ancestor simulations so detailed, the odds we're living in base reality are vanishingly small. And if we are in a simulation, time might not be the immutable force we assume, but a dynamic parameter that can be tweaked, paused, or even rewound. Think of how video games handle time. In open-world games, time often accelerates. A minute of real life becomes an hour in-game, compressing days into minutes when the player sleeps. Now scale that up. What if our universe's apparent 14 billion-year history was generated last Tuesday, complete with fossil records and cosmic background radiation? Or consider save states, moments where the simulation resets to a prior configuration. Could déjà vu or the Mandela effect, where large groups misremember historical details like Nelson Mandela dying in prison, be glitches where the simulation loaded an older version of events? Even physics offers curious hints. Quantum indeterminacy, where particles exist in probability states until observed, reads suspiciously like a rendering optimization, only calculating definite properties when necessary to save processing power. The Planck length and speed of light might be processing limits, preventing infinite precision that would crash the system. Even time dilation near black holes could mirror lag in an overloaded server struggling to compute extreme gravitational fields. Yet skeptics counter that absence of proof isn't proof of absence. The universe's staggering consistency, physical laws holding firm across billions of light years, suggests either an impeccably coded simulation or a genuinely fundamental reality. And if we are in a simulation, how could we ever distinguish a glitch from an unknown natural phenomenon? The very rules preventing us from detecting the simulation would be part of its design. Perhaps the most haunting implication isn't whether time is simulated, but what it means if we ever proved it was. Would discovering our universe's code grant godlike control over time, or reveal we're locked in a sandbox with no admin access? Either way, simulation theory forces us to confront that time's nature might not be written in the stars, but in someone else's source files. What if the Big Bang wasn't the true beginning, just a violent turning point in an endless cosmic cycle? The question of what came before time itself has haunted physicists for decades, and the answers they've found are stranger than fiction. Loop quantum cosmology dares to propose that our universe wasn't born from nothingness, but from the collapse of a previous cosmos, a cosmic rebound where time didn't start but reset. Picture a black hole's crushing gravity not as an end but as a cosmic reset button. When the collapsing universe reaches a certain density, quantum effects kick in like a trampoline, bouncing space-time outward into a new expansion. In this model, the Big Bang becomes the Big Bounce, and time stretches infinitely in both directions, no true beginning or end in sight. Stephen Hawking took a different approach with his no-boundary proposal, a mathematical sleight of hand that sidesteps the need for a time zero altogether. Imagine Earth's North Pole. There's no point north of it, yet the concept of before the pole loses meaning. Hawking and James Hartle suggested the universe works similarly, with time behaving like a dimension that gently curves into space at the Big Bang, forming a smooth, four-dimensional sphere without edges. Here, asking what happened before the Big Bang is like asking what's north of the North Pole, a question that doesn't compute because the framework for before didn't exist yet. Hawking's most radical twist was the introduction of imaginary time, a mathematical construct where time acts like a fourth spatial dimension. In this strange landscape, the Big Bang isn't a fiery explosion but a geometric feature, a point where imaginary time seamlessly blends with space, like the base of a wine glass merging into its stem. While imaginary time isn't real in the traditional sense, it elegantly wipes away the singularity problem, offering equations that describe the universe's birth without infinities or breakdowns in physics. Yet these theories all collide with the same paradox. Our brains are wired to think in terms of cause and effect, beginnings and endings. The very language we use stumbles when trying to describe a reality where time loops, curves, or vanishes entirely. Even the word before becomes a trap when applied to the Big Bang, a moment when the rules of time as we know them may have blinked into existence, the most humbling possibility. Time itself might be an emergent property, a side effect of deeper physics we haven't yet uncovered. Like a fish trying to comprehend water, we're limited by the very dimension we're attempting to study. Whether the universe cycled, curved, or computed itself into being, one thing's certain: the true nature of time's origin remains the ultimate cosmic detective story, with clues hidden in quantum gravity, black holes, and the faint echoes of the universe's first moments. And until we crack the case, the question lingers not just how time began, but whether beginning is even the right word at all. Picture standing on a train platform as a high-speed locomotive rockets past you at nearly the speed of light. A clock mounted on the train flashes its time as it speeds by, and to your eyes, it appears to tick slower than your own watch, a textbook example of time dilation. But here's where things get mind-bending. To a passenger sitting inside that train, you're the one moving and your clock appears to crawl. This paradox isn't just a quirk of relativity. It's the linchpin of the Retake-Putnam argument, a philosophical proof that all moments in time, past, present, and future, are equally real. The argument hinges on relativity's ruthless demolition of absolute simultaneity. Two events that appear simultaneous to you, say, lightning striking both ends of the train, won't be simultaneous to the passenger whizzing past. Their motion warps their perception of now, slicing spacetime differently. Dutch physicist Cornelis Retake and philosopher Hilary Putnam took this further. If now is observer-dependent, then every moment must exist in some frame of reference. There's no privileged present that everyone agrees on, no universal clock ticking for the cosmos. Instead, reality resembles a vast block where every event, from Caesar's assassination to the heat death of the universe, is frozen in place like exhibits in a museum, always there, just not always your now. To visualize this, imagine the train isn't just passing you but zooming toward a distant supernova. As it accelerates, the passenger's now slices spacetime at an angle, skewing their perception of events. A supernova that hasn't yet exploded in your frame might already be a fading ember in theirs, but here's the kicker: neither perspective is wrong. Relativity insists both are equally valid. So if the passenger's now includes the supernova's aftermath while yours doesn't, how can the explosion's outcome be unreal for you? The only consistent answer, Retake and Putnam argue, is that all events exist timelessly across spacetime, with observers merely spotlighting different cross-sections. This flips our intuitive sense of time's flow on its head. If the future is already out there, lurking in some reference frames, does free will evaporate? Not necessarily. Eternalism doesn't dictate what happens, only that every moment is a fixed coordinate in the cosmic block. Your choices still shape your path through this landscape, like a hiker deciding which trail to follow on a pre-existing mountain. The implications ripple beyond philosophy. GPS satellites must account for relativistic effects, proving observer-dependent time isn't abstract math but real-world engineering. And if eternalism holds, it could redefine how we think about black holes, quantum states, even consciousness itself. After all, if the past isn't gone and the future isn't unwritten, reality might be less like a river and more like a novel, where every chapter exists simultaneously and we're just turning the pages. String theory doesn't just add extra dimensions to space, it weaves time into a tapestry of hidden layers, turning our four-dimensional reality into a tiny sliver of something far grander. Imagine the universe as a symphony where the notes we hear are just 3 dimensions of space and 1 of time, while the full melody plays across 10 or even 26 dimensions, curled into shapes so tiny and complex we'd never perceive them. These hidden dimensions aren't just spatial, some might be temporal, folding time itself into geometries beyond our comprehension. At the heart of this idea lie Calabi-Yau manifolds, six-dimensional shapes so intricate they look like quantum origami, twisting space and time into patterns that could explain everything from particle masses to the nature of dark energy. Picture a garden hose stretched across a field. From a distance, it appears as a simple line, one dimension, but up close you see its circular surface, a second dimension curled tightly around the first. String theory's extra dimensions are like that, but with far more complexity. Calabi-Yau manifolds could tuck multiple dimensions of time into these folds, creating structures where causality operates differently. In such a universe, time might not flow in a single direction but branch like roots underground, with every possible path existing simultaneously. These hidden temporal layers could resolve paradoxes in quantum mechanics, offering a playground where particles communicate across time loops or entangled states span dimensions we can't see. The catch: proving any of this is staggeringly difficult. If extra dimensions exist, they're likely compactified, curled up at scales a billionth of a billionth the size of an atom. Testing their influence would require energies far beyond our particle colliders or detectors sensitive enough to catch whispers from these hidden realms. Some theorists propose looking for cosmic fingerprints, anomalies in gravitational waves or quantum entanglement that betray the presence of extra dimensions. Others suggest that if time operates differently at these scales, tiny discrepancies in atomic clocks or neutrino oscillations might reveal cracks in our four-dimensional illusion. String theory's critics argue that without experimental evidence, it's more metaphysics than physics, a beautiful mathematical castle floating in the air. Yet its defenders counter that every revolutionary theory once seemed untestable, from black holes to the Higgs boson. Whether these hidden dimensions of time are real or not, they force us to confront a humbling truth. The universe's true structure might be as alien to us as a smartphone would be to Neanderthals, an architecture so advanced we're only beginning to guess at its blueprints. Imagine a frothing ocean where each bubble is an entire universe, budding off from an endlessly inflating cosmic foam. This is the inflationary multiverse, a landscape where time itself splinters into countless different flows. According to eternal inflation theory, the Big Bang wasn't a one-time event but the explosive birth of one bubble in a vast, ever-expanding quantum sea. And here's where it gets wild. Each of these bubble universes could operate under its own rules of physics, with time moving at different speeds, directions, or even dimensions. One universe might experience time as a linear arrow, while another sees it as a branching tree or a closed loop. This solves one of cosmology's biggest puzzles: fine-tuning. Our universe's constant gravity's strength, the speed of light, the mass of electrons are eerily perfect for life. Tweak any one, and stars wouldn't ignite, atoms wouldn't form, and existence as we know it would be impossible. The multiverse offers an elegant explanation. With infinite bubbles, every possible configuration exists somewhere. We just happen to inhabit the rare bubble where conditions allow us to ponder the question. It's like winning the cosmic lottery, not because the odds were in our favor, but because every possible ticket was printed. But this inflationary sprawl births paradoxes even stranger than the ones it resolves. If time flows differently in other bubbles, could some universes experience causality backward? Picture a world where fire cools wood into logs or rain rises from puddles to clouds. Worse, if bubbles collide, as some models suggest, could a universe with reverse entropy bleed into ours, scrambling time's arrow like a shattered hourglass? The math allows it, but our intuition recoils. Then there's the measurement problem. Without a shared clock across the multiverse, how do we compare time's passage between bubbles? A second here might be an eon there, rendering notions of simultaneity meaningless. even consciousness might fracture. A version of you in a fast-time bubble could live and die before your next heartbeat here, raising unsettling questions about identity and existence. Yet for all its chaos, the inflationary multiverse hints at a deeper order. Like a kaleidoscope turning randomness into patterns, it suggests that time's diversity isn't a bug but a feature, a necessary spectrum for reality's full expression. Whether we're one thread in this tapestry or its sole observers remains the ultimate mystery, waiting in the voids between the bubbles. Black holes have long been the ultimate cosmic paradox, objects so dense they trap light, yet somehow leak radiation, regions where time grinds to a halt, yet chaos reigns supreme. Now imagine dropping a time crystal into this gravitational madness. These bizarre structures, which pulse in perfect rhythm without energy input, would face their ultimate test near a singularity. The usual rules like entropy's relentless rise might not apply here. Instead, time crystals could become cosmic metronomes, their oscillations warped by spacetime's extreme curvature into patterns that defy intuition. Picture a dancer pirouetting on the edge of a whirlpool, their movements distorted but never broken, an eternal rhythm surviving even as the universe tears itself apart. Hawking radiation adds another layer of strangeness, as virtual particles split near the event horizon, with one falling in and the other escaping. Black holes slowly evaporate. But what if time crystals interact with this quantum sleight of hand? Their unbreakable cycles might imprint on the radiation, leaving faint echoes in the emitted particles. It's like dropping a vibrating tuning fork into a storm. The storm rages, but the fork's hum lingers, detectable in the chaos. Some theorists suggest this could resolve the infamous firewall paradox, where quantum mechanics and relativity clash over whether an unlucky astronaut crossing the event horizon would be incinerated. If time crystals stabilize the quantum vacuum near the horizon, they might smooth out the lethal energy spikes, acting as cosmic shock absorbers in the most violent region of spacetime. Yet the wildest possibility lies in the singularity itself. General relativity predicts infinite density, but quantum gravity hints at something stranger, a Planck-sized nugget where time and space lose meaning. Here, a time crystal's oscillations might not just persist but amplify, resonating with the underlying quantum foam. Imagine a drumhead vibrating at the center of a tornado, its beat somehow dictating the storm's structure. If true, time crystals could be the missing link between quantum mechanics and black hole interiors, revealing how information survives the singularity's shredding grip. Of course, testing this is another matter. Black holes don't exactly welcome probes, and time crystals are fragile, lab-bound curiosities. But future telescopes analyzing Hawking radiation for anomalies or quantum simulators modeling extreme spacetime might uncover hints. Whether time crystals illuminate black holes' secrets or deepen their mysteries, one thing's clear: the marriage of these two enigmas pushes physics to the edge of comprehension, where even time itself becomes a flickering shadow in the void. What if the future isn't just unwritten, but actively reaching back to shape the past? Yakia Aharonov's time-symmetric quantum mechanics dares to suggest exactly that: a universe where causality isn't a one-way street, but a tangled web where tomorrow's events whisper into yesterday's ears. This isn't science fiction. It's a rigorous mathematical framework called the two-state vector formalism, where quantum systems are described not just by their past states, but by future boundary conditions too. Imagine rolling a ball down a hill, only to discover its final landing spot somehow guided its initial push. That's the level of temporal weirdness we're dealing with here. Aharonov's theory flips the traditional quantum script. Instead of a wave function collapsing from past to future, it proposes two waves meeting in the present, one evolving forward from the past, the other backward from the future. Picture two ripples colliding in a pond. Their interaction defines the now we experience. This explains bizarre quantum phenomena like the delayed choice experiment, where a photon's past behavior changes based on future measurements. In Aharonov's view, the photon isn't retroactively changing. It was always responding to both past and future constraints, like a dancer mid-performance who knows the finale before the first step. The implications for free will are staggering. If future events constrain past states, does that mean our choices today are nudged by a destiny that's already unfolding? Philosophers split sharply. Some argue this is just complex causality, like a chess player thinking 10 moves ahead, where the future, their plan, influences present moves. Others see a darker determinism, where the universe is a locked puzzle and our sense of agency is illusionary. Yet Aharonov himself rejected fatalism, insisting retrocausality doesn't eliminate free will, it redefines it. Decisions might ripple both ways, but the present moment remains where past and future negotiate, leaving room for genuine choice. Critics counter that retrocausality violates our deepest intuitions about cause and effect. How can an effect precede its cause without unraveling reality? But supporters point to quantum weirdness entanglement, superposition as proof that intuition is a poor guide at fundamental scales. After all, if particles can be in two places at once, why can't causes loop backward? Experiments weakly measuring pre- and post-selected quantum states have even found hints of particles sensing future constraints, like shadows of events that haven't happened yet. The debate rages on, but one thing's clear: Aharonov's vision doesn't just tweak quantum mechanics, it upends our linear storytelling of reality. Whether time's arrow is truly reversible or just more flexible than we thought, this theory forces us to confront that the universe might not care which direction we call forward. And in that cosmic indifference lies a humbling truth: the flow of time, like so much else in quantum realms, might be another illusion waiting to dissolve under scrutiny. What if time isn't just a backdrop to consciousness but a construct woven by the mind itself? This unsettling idea bridges physics and philosophy, suggesting that without an observer, time might not exist as we know it. Edmund Husserl, the father of phenomenology, shattered conventional views by proposing that time isn't an external river but a structure built by our perception. Imagine listening to a melody. You don't hear individual notes frozen in isolation, but a flowing unity where past tones linger, present notes resonate, and future ones are anticipated. Husserl called this time consciousness, the mind's ability to stitch discrete moments into a seamless stream. It's as if the brain is a composer, constantly rewriting the score of reality to create the illusion of continuity. Modern neuroscience echoes this in integrated information theory, which posits that consciousness arises from the brain's ability to integrate vast amounts of information across time. Think of your brain as a symphony conductor, blending sensory input, memory, and prediction into a unified experience. When you touch a hot stove, the pain isn't just a momentary signal, it's a temporal arc linking the initial shock, the recoil, and the lingering ache. IIT argues that the more interconnected these moments are, the richer the conscious experience. Time, in this view, isn't a passive dimension but an active construction, a byproduct of the brain's relentless synthesis. But does time exist outside observers? Quantum mechanics muddies the waters. In the delayed choice experiment, a particle's past behavior changes based on future measurements, as if reality waits for an observer to choose its history. This aligns with Husserl's idea that time isn't objective but arises from interaction. Even the universe's low entropy at the Big Bang, a prerequisite for time's arrow, might hint at an observer-dependent reality. Cosmologist Lee Smolin speculates that time could be fundamental only in contexts where complex systems like brains evolved to perceive it. In empty space or a lifeless cosmos, time might dissolve into meaningless fluctuations like a clock without hands. Critics counter that time's mathematical structure in physics, from relativity's spacetime to quantum clocks, operates independently of minds. Yet the debate reveals a deeper truth: time might be a layered phenomenon. At the quantum level, it could be a web of probabilities, in conscious beings a flowing narrative, and in the cosmos an emergent property of entropy. The real mystery isn't just what time is, but why we experience it so vividly, a fusion of physics, biology, and perhaps something even more profound. After all, if a tree falls in a forest with no one to hear it, does it make a sound? The harder question: if no one's there to remember, did time pass at all? What if the universe isn't just expanding but evolving toward an ultimate moment of infinite knowledge and power? This staggering vision lies at the heart of the omega point theory, proposed by physicist Frank Tipler, who dared to merge cosmology with theology in a way that left both scientists and philosophers reeling. Picture a future so distant that all matter and energy have collapsed into a final, unimaginable singularity, not just an end but a transcendence. In Tipler's framework, this isn't the heat death of randomness but a cosmic crescendo where intelligence becomes omnipotent, omnipresent, and in a sense divine. Tipler's math hinges on a closed universe, one where gravity eventually halts expansion and pulls everything back in a big crunch. As the cosmos contracts, the energy density skyrockets, enabling civilizations of the far future to harness infinite computational power. Advanced beings could simulate every possible consciousness, resurrecting every mind that ever existed through sheer information processing. It's a twist on the simulation hypothesis, but with a theological bent. The omega point isn't just a supercomputer, it's God in the most literal, physical sense, emerging from the laws of physics rather than the pages of scripture. The echoes of theologian Pierre Teilhard de Chardin are unmistakable. Decades before Tipler, Teilhard envisioned an omega point where evolution culminated in a spiritual unity with the divine. Tipler's version swaps mysticism for quantum mechanics, arguing that resurrection is technically feasible via quantum state reconstruction. Every thought, every memory, every flicker of consciousness could, in principle, be recreated atom by atom in this ultimate singularity. It's immortality not through faith but through thermodynamics and relativity. Critics, however, have torn into Tipler's assumptions. Modern observations overwhelmingly favor an open universe, one that expands forever into cold, empty darkness, not a dramatic collapse. Dark energy's relentless push makes a big crunch increasingly unlikely. Even if the universe were closed, the timescales involved are so vast that the idea of civilizations surviving to manipulate the collapse borders on fantasy. Nobel laureate Steven Weinberg dismissed the omega point as a fantasy of immortality projected onto the laws of physics, while others accused Tipler of cherry-picking equations to fit a quasi-religious narrative. Yet the theory's boldness forces us to ask profound questions. If intelligence can shape cosmic-scale events, could the universe be self-designing its own destiny? And if the omega point were possible, would it blur the line between physics and theology so completely that science and spirituality become two languages describing the same reality? Whether a groundbreaking insight or a grand overreach, Tipler's vision lingers as a haunting reminder that even in the coldest equations, we might find the faintest echoes of eternity. From the timeless block universe to the quantum entanglement of past and future, each theory we've explored today cracks open another door in our understanding of reality. The notion that time could be a fifth dimension, a digital construct, or even an illusion woven by our own consciousness isn't just speculative. It's a challenge to everything we take for granted. Consider the audacity of these ideas: universes branching with every decision, black holes echoing with the rhythms of time crystals, or the haunting possibility that our entire timeline is but one thread in an infinite cosmic tapestry. Physics has peeled back layer after layer, revealing a universe far stranger than our ancestors ever dreamed. What's truly astonishing is how these theories aren't just abstract musings. They're grounded in math, observation, and experiments that push the boundaries of human ingenuity. The delayed choice quantum eraser, the precision of atomic clocks in orbit, even the whispers of gravitational waves, all hint at a reality where time is more fluid, more malleable, and more mysterious than we ever imagined. And yet, for all our progress, the most fundamental questions remain unanswered. Does time truly flow, or is it a stubborn illusion etched into our perception by the wiring of our brains? Are we passengers on a one-way journey, or actors in a cosmic play where every scene exists simultaneously? So where does that leave us? Perhaps the most exhilarating takeaway is that the mystery isn't solved, it's deepening. Every discovery peels back another layer, revealing new riddles waiting to be unraveled. Maybe the answer lies in the fabric of spacetime itself, or in the quantum vibrations of particles we've yet to detect. Or perhaps, as some theories suggest, time isn't something to be unlocked at all, just a story we tell ourselves to make sense of a universe that operates on rules we're only beginning to glimpse. As you step away from this journey, let these ideas linger. Which theory resonated most with you? The eerie symmetry of eternalism, the chaotic branching of the multiverse, or the haunting simplicity of presentism, where only this very moment is real? Whatever your take, one thing's certain: the nature of time is the ultimate puzzle, and we're all pieces of it. So stay curious, keep questioning, and join us next time as we dive into even more cosmic enigmas. Until then, here's a final thought to ponder. If time isn't what we think, what else about reality might be waiting to surprise us?